Alright, guys, I am back for the new year uploading videos. Cringe or not, we are back. Um, yeah, so we're gonna look at this problem called graph cost. Um, this is actually surprisingly not that bad of a div 2e. Usually you would think div 2e's are pretty bad, but this one's actually not that bad. So I only did like these three problems. I didn't bother like do A or B because like kind of a waste of time. But yeah. So don't get scared because it's a Div 2E. It could actually be like understandable and you can learn something, which is what I did. My submissions are kind of cringe over here. Yeah, it only took me like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's fine. But we understand the problem, and I'm going to represent it, or I'm going to explain the problem. So this is a question. You are given an initially empty undirected graph with n nodes numbered from 1 to n. You want to add m edges to the graph so the graph won't contain any self loops or multiple edges. If an edge connecting two nodes u and v is added, its weight must be equal to the greatest common divisor of u and v, GCD UV. In order to add these edges to the graph, you can repeat the following process any number of times, possibly zero. Choose an integer k greater than 1. And when you choose this integer, you can add exactly k edges to the graph. But here's the caveat. Each of those edges have to have a weight of k plus 1. And the idea is that you can only connect an edge between two nodes if the weight of that edge is the GCD of u and v. And you can just read the rest. It's a pretty self-explanatory problem in terms of like what it's saying, and then the goal is to minimize the cost of this of the graph of n vertices and exactly m edges. Now don't worry about the trolling on the implementation. I was just being very stupid, very stupid. But this question logically is actually not too bad, and I'm going to show you how you could sort of like approach this problem, because there's something very interesting about this problem. Like, so if you like just read the before you even look at test cases, right? If you just read the question and it says like this line, right? Add exactly k edges to the graph, each having a weight of k plus one, and then adding these k edges costs k plus one. Like, why? You would sort of have this intuition of why is it k plus one? Why not just k? Like, does this plus one really make any difference in the difficulty of the problem? So I think that's sort of an intuitive question you would ask yourselves. And so, in fact, the plus one actually does make a difference in difficulty of the problem, because if it was just k, let's just say we change this problem, right? The weight doesn't really matter. The weight constraint only matters in terms of the GCD stuff, and we'll worry about that later. But in terms of the cost, right? If the cost, if it said k plus one versus k, it would actually be different problems, right? Let's look at the problem if it just said k, right? How would the problem be, right? Well, if it just said k, then the cost would either be m or negative one, right? Because the idea is that like if you can like okay, let's say we have six nodes or something, or six pairs, or yeah, six nodes, six edges to fill, right? Because let's say m is six, right? On the first operation we might do two. If k is if on the first operation we might add two edges, and we're gonna do the case where it's not k plus one, the cost is k. So if we add two edges, we'll just say the cost is two, and then on the second operation we might do four, and then the cost would be four. So you realize that like if in order to fulfill the entire graph, if this question was just costing k, not k plus one, then it would just to fill the entire graph, but also you want to fill the entire graph to m edges. At the same time, it would also fill the entire cost to m, if you can do it. If you can't fill the entire graph to m edges, then the answer is just negative one, but that's just the impossible case. We don't really care. That's just something we would just worry about in code. But the idea is that, like, okay, if this question just said adding these k edges cost k in total, well, then it wouldn't really be an interesting problem, because you would just every time you add a certain amount of edges to get to m, you add the cost is the amount of edges you added. So in the end of it all, if you can get to that full graph, it would just cost m, right? I think that's a very obvious thing. And so you're wondering, well, damn. So that's trivial. So then what makes k plus one harder? What makes k plus one harder is that, let's do the same thing here, right? Let's say we do the same thing. We do like one, and then we take two edges. If we take two edges, that's implying k is 2. So then if we actually do the actual problem, we add the cost would be 3. And then 2 for the cost would be, in fact, I would actually I'm going to write this as 2 plus 1. You'll see why. And then the cost would be 4 plus 1. So the idea is that the difference between these problems is the extra ones added onto it. And this sums up to the amount. This is no coincidence that it sums up to this. So it looks like if we do k plus 1, then it's basically the equals the k cost problem, where this is k. It's basically the k cost problem, except the cost is that plus the amount of operations you do. So if you do like 3 operations, like if I did 3 operations, so we were trying to form 6, so maybe I could do 2 here, 3 here, and 1 here, then it would be, if you did the k cost problem, it would just be 2, 3, 1. It would add up to 6. But if you did the k plus 1 cost problem, right, it would be plus 1, plus 1, plus 1, plus 1. So it would just be the amount of operations you do. So the idea is that, well, if you want to minimize the cost, isn't it just effectively the same thing as minimizing the amount of operations? That's basically it. So from this observation alone, you sort of solve the problem almost, right? Because you notice a very huge observation. Uh, to minimize the cost is the same thing as minimizing the cost is directly proportional to minimizing the amount of operations to fill the graph. So in essence, the cost equals operations. Basically, to minimize cost equals minimize operations. In essence, this is what we're doing. So the idea is that you can forget about, like, you can sort of just forget about uh this the cost thing, right? The cost thing can just come naturally, right, at the end, because the idea is that you want to minimize the number of operations. How would you minimize the number of operations? Well, to minimize the number of operations, you're trying to fill m first, right? You're trying to fill the graph as fast as you can. So you want to add as many edges as you can at every instance, right? So if you can add, let's say you're trying to fill m edges, right? So you know that the operations you can do is up to n, right? Or well, there's okay, whatever. Well, let's say, well, you can add, let's say, whatever. So if you can add m edges, you would add m edges, right? Let's say let's say these are all the values you can add. So let's just start with like I'll start with some value I, and then these are just I minus 1, I minus 2. Let's say these are just some values that we can add. Well, then, since I is the highest, well, then I'll just do this operation. I'll do operation when k is equal to I, because that operation is going to give me the most edges. So the idea is that you always pick a k such that k is the highest, because if k is the highest, then you'll just sum up to m, as you'll get to m as fast as you can. So it's actually really simple. Just greedily. Oops, what is this? What is that? Okay. Okay. Just greedily take the operation type with the highest amount of edges added. That's really the solution. I think you don't really need to prove this greedy, but if you want to prove this, like if you're just extra like me, well, this isn't too hard to prove, right? Like, let's say we have the number 10, right? And we have access to the numbers 5, 4, 3, 2, 1. Because the idea is that basically you're going to have access to the numbers. Wait, hold up. Yeah. You're going to have access to the numbers 1 to n, and you're gonna be trying to form m. So you have access to the numbers 1 to n, right? So let's say m is equal to 10, right? And we're gonna looking at the case where m is equal to 10. and is equal to 5, a random case, you're gonna have access to all these numbers. And basically, like what the question now is, what we've reduced it just by this observation, is that like, okay, we'll just uh, uh, pick these numbers in this array such that like it sums up to m, and you want to pick the smallest amount of numbers possible. So you want to, if you can do this in like three numbers, then you're chilling. If you can do it in one number, you're chilling. That's basically what you're gonna do. And so if you look at this case, if we're just trying to pick numbers so that it sums up to 10, I would obviously start, and we're trying to minimize the number of numbers involved. I would obviously just start with 5, and then I would start with 4, and then I would get 1, right? The idea is that like when you pick these numbers, you don't have to worry about like there's always going to be a number available, right? Like if you pick 5, then you need 5 left, but you can just pick the next highest. And if it takes you over it, right? Let's say it was 8, right? Then if you pick 5, then okay, you can't pick 4 because it takes you over it, but then you can just pick 3, right? So you're just picking the next possible number you can take, the highest possible number you can take each time, and you'll obviously just get to m. Like this is actually just very trivial, and I don't think you need to like full out prove it. um it's just always going to be possible to, if it's possible, this will never miss any solutions. Taking the highest at every instance will never miss any solutions such that the numbers sum up to m. It will never miss any solutions because like if you take x, well then like it just doesn't miss any solutions because you have access to all these numbers. It's not like I don't have it's not like when I take 5 and, because like okay, let's say we want to form 10, and let's say I take 5 and 4. When I take 5 and 4, right, it's not like I lose access to 1, right? It's not like this would only be a problem if 1 wasn't existing in this array, but it is existing in this array because we can choose any. The operation says we can choose any k, so we can choose any number from like 1 to n as our k, and we can add that many edges or whatever. Yeah, that's effectively just it. That is it, right? But there's one little nuance which is sort of not really a nuance, because if you don't know how to do it, then you can't really solve the problem. Is how the heck are we gonna worry about this GCD thing? So this GCD condition, like we know that, okay, what I would do is, let's say I was working on a case 6 and 10. So this is n equals 6, and so there's 6 nodes, and we're trying to add 10 edges. Well, then I would just try to add okay, well, we're trying to add 10 edges, so um, let me just add. Then what I would do is I would see, can I add? Can I just pick an operation k equals 10 because that would add 10 edges, right? You can't do that because then you would be adding 10 edges. If you pick in this test case, if you pick an operation k equals 10, you'd be adding 10 edges of weight 11. But the GCD from numbers 1 to n, because remember, these are just the nodes, right? If you look at the numbers from 1 to 10, there's no if you pick any arbitrary pair from these numbers, the GCD of those will obviously not be 11, right? The highest number is 10. That could be impossible. So the idea is that like it's not we're not done yet. We still need to figure out a way to see if it's possible to take a number. So how do we know if it's possible to take a number? Well, if let's say I want to take the number 10, right? I need to find. Let's say I want to do the operation k. Let's say I want to take the operation k, right? Right. So let's say I want to take operation k. Let's do this. Let's say I want to take operation k. So if I want to take operation k, then the idea is that if you want to take operation k, then you know that you have to add k edges with weight k plus 1, right? This is the problem. So the question is, how many pairs of nodes, values from 1 to n, have a GCD of k plus 1? Because you know that you can only add those edges if the GCD is the same as, if the weight of that edge is the same as the GCD between those two values from 1 to n. So this is a natural question that merges, right? For a operation k, we want to know the above question. So in general, we want to know. In general, we want to know for x, for some x in 1 to n, how many pairs of numbers in that range have GCD X? That's a question, right? We can do this with dynamic programming. Basically, you know that you can use like principle of inclusion exclusion, right? Whatever. So like if you want to check let's say DP at I, define DP at I. So define DP at I as the number of pairs of number as the answer. Okay, let me just do x. Define dp of x as the answer to the question, and we can initialize as dp of x to this. So let me dp of x can be equal to n of 4 minus something. So basically, what I'm doing is that the amount of multiples. So what we can do is right. Well, if we know that it has a if we know that it has a GCD of x, well then we know that the two numbers being involved are obviously multiples of x, right? If it has a GCD of x, right? Both if the greatest common divisor both numbers is a GCD of x, well then they're obviously multiples of x. So what we can do is we can basically choose any two multiples of x, but we realize that like this is not enough. This overcounts it because just because you have like let's say you can have a multiple of two, right? Just because they're both multiples of two doesn't mean the GCD is two. So this obviously overcounts it, right? Because basically what happens is that the something would have to be like this. You would have to subtract like all the ones that have all the ones you would have to subtract um the ones that are like that have a you would have to subtract this and then this and then dp and I think it's n over to this. I don't really care about the nuance here, or just do to dpy, or I'll use something. You would have to subtract this, right? This is easier to think of, right? Because the idea is that like okay, you've already included all the multiples, um, and then if you choose any two, well then that's going to overcount because what about the ones that have a GCD of 2x? They're obviously and 3x and 4x, 5x, and then all the way to y, such that this condition is true. Or secondly, it's this, right? So yeah, that's basically it, right? You have to subtract this. So then you know that this is the dp. And the base case is that dp of n is 0 because obviously no any pair of numbers will have a GCD of n because n is the highest number, so that's impossible. But yeah, this is basically the dynamic programming thing, and this you can do this in n log n time. I think it's like I don't really want to prove why it's n log n, but like it's sort of obvious because like it's obviously less than n squared, so like it's sort of intuitively n log n, but like I don't really care. Apparently, this is a standard trick, right? So this is a kind of a generic question. So you can just accept that it's n log n, right? Whatever. It's and it's it just happens to be fast enough. Yeah, that is effectively it. And we can look at the code. This is the code. So the code here is we're gonna take in n and m, and then we're gonna set our answer to remember to use longs. Just use longs. Literally, just don't take any chances. Anytime you sum up, multiply stuff, just use longs. Right? I like still have to learn my lesson, even though I've been coding, I guess, for like I don't know. Okay, but like so you want to initialize. Okay, this is a trivial thing. Like you don't need to do this because like Java is already initialized to zero. But I kind of want to enforce the base case, like just enforce it in my mind. So then you want to do the DP, right? You know that this is just the formula. It's basically doing the same thing here. And then you want to keep track of the edges used, right? Per and the operation type you want is this stuff you kind of have to think. This is like a nuance you have to think of the code for me, at least the way I coded it. So you want to make sure that like you know that you can't your operation type can't be like more than n because there's no way that the GCD is gonna be like if let's say your operation is k and it's k plus one, make sure that k plus one is not greater than n because there's no way that any numbers have a GCD of greater than n because all the numbers are smaller than n. So just make sure that you start with like n minus one because here you'll just add one and you don't want this is just for like out of bounds exceptions. You have to think of that. It's just sort of the annoying thing. Um, but then, yeah, you just keep track while the edges used is less than n, and the operation type, this is just like the k. This is operation type. Just think of operation type as k. Then you just if the edges if the ed n minus edges uses the edges left. If the edges left is zero, then it's filled and you can break. I don't know if this is needed, but I just did it because it was whatever. And then if there's none, if you can't use any edges, just go to the next operation and continue. And then the edges taken in an operation is this is like sort of the nuance you have to think of again. The edges left, right? The edges left you have divided by the operation type times the operation type. So this is like sort of nuanced stuff that you have to think of. But just think about like you okay, I don't really want to explain this because like you could just code this yourself if you understand the logic of the problem. But yeah, this is just sort of how you calculate the edges taken with this dynamic programming thing. And then you just add the edges taken over the operation type. This is going to add the amount of operations you use per. So like for per k, because think of operation type as k per k value that you're on, then the amount of operations you used in for that k value is the amount of edges taken divided by the amount of edges provided by that operation type, obviously. And then edges used is just this, and yeah, this is just the code. Like I recommend you don't because this is my own code. I recommend you just code your own, right? Um, but yeah, and then you print out the edges used, and if the edges is m, then you can print out the answer. If it's not, then you can't. But yeah.